Okay, so welcome everybody to this month's APS GPC seminar. Our speaker today is David Marshall from Oxford University. Um, so before we go on, I'll just say this is being recorded. We'll record till until the start of questions. If you have questions, please during the talk, please just drop them in the chat, and we'll monitor them. If there's anything that seems really pertinent, we'll bring it up. Otherwise, we'll respond to them at the end of the talk. So today's speaker is Professor David Marshall from Oxford University. Just a brief background. David got his undergraduate in physics at Imperial College. And then after a brief flirtation, apparently with high energy physics, recovered his sanity and did a graduate degree in physical oceanography, also at Imperial. Then after a postdoc at MIT, he joined the faculty first at the University of Reading, and then moved on to Oxford in the physics department, where he sits now. I think one of the rare places where physics sits in, where oceans and atmosphere work sits in physics. He's a fellow of the Institute of Physics and received the Appleton Medal from them, and he has a higher Erdős-Bacon Sabbath number than Natalie Portman at 9. And without further ado, I will let him pop up the slides and tell us about the oceans.
I wasn't expecting the Natalie Portman reference. Sorry, what did you say?
Portman has 11. You have 9.
Oh, wow. Okay. Right. I'm going to share. So first of all, well, let me share the slide first because I can't multitask. It would be better if I did it the other way around. So I press that button, then Keynote, share, and then I will go full screen. That works. Beautiful. So you guys can see the main slides, I hope, at this point.
Mm-hmm. Yes.
And I've got another pop-up window that is blocking my view, so I will just move that out of the way. So first of all, big thank you to the committee, especially Albion and Qing Yao for inviting me to give this talk. When I got the invitation, actually, what really appealed to me was the sort of wider goal of these talks, which is to try and introduce the broader physics community to fundamentals of climate science, and to try and encourage more physics undergrads and grads to pursue research and career opportunities in climate science. So I've taken the instructions at face value here, and I will talk quite a bit at the beginning and a little at the end about my views on education, links to physics, and also how I got into the field. Because it's kind of interesting, I think, and often quite random, actually. I think how these things come to pass. I've seen a few distinguished colleagues joining this talk. I am going to treat this talk very much as a sort of tutorial, as I was instructed to, onto the basics of ocean eddies and review work I've been doing over the last 15 years or so. Now, so it really is pitched, and I hope in a way that that those of you who have never thought about ocean eddies can at least try and understand the broad concepts. So I'm going to talk about the physics of ocean eddies and their impact on global ocean circulation. This is work I've done with an awful lot of people who I mentioned during the talk, but especially James Madison, Julian Mack, but many others too. The image we're looking at here is of the Antarctic circumpolar current. I think it's from a model, and you're looking at surface current speed, essentially. And what I hope you can see is both a large-scale current, but an awful lot of small-scale structure embedded within the larger-scale flow. Before I move on to talk about this problem, just a little bit of background. So I did my first degree in physics at Imperial College London. I saw Alistair Adcroft on the a couple of minutes ago had joined us. So he and I were both graduate students at Imperial. Actually, my route into physics starts a year earlier, really, because I interviewed at Cambridge for natural sciences, and I did get an offer, but I must say I absolutely hated the experience at the time. Coming from a a state school, as we so a comprehensive school, as we call them in the UK. I really wasn't ready at that stage or prepared for the Oxbridge experience. And when I interviewed at Imperial and got a very low offer in terms of the grades I needed to achieve, this was just wonderful. I really wanted to come to London, and it's one of the best decisions I ever made. I really set my heart on working on theoretical physics. I was, like a lot of people, I kind of got seduced by classical mechanics, quantum mechanics, general relativity, and so forth. And in my final year, one of the courses I took was astrophysics. And that particular year, nothing against astrophysics, it was just really badly taught and the exam was quite hard. And so I decided I'd look around for an easier sort of 8th exam to take. And I stumbled on the atmospheric physics paper and thought it looked quite a bit like plasma physics, which I was already taking. So I decided I would do that. And so I went along to the lectures by my namesake, but not relation, John Marshall. And it was an absolute blast. I just loved it. And so much so over the summer, I began to think maybe I'd made the wrong decision. Anyway, 3 years later, I moved to the University of Southampton to start a PhD in quantum chromodynamics. I think I knew at the moment I arrived on a very rainy, sort of wet, cold Sunday evening in suburban Southampton. I'd made the wrong choice, to be honest. And on the Monday afternoon, I called up John Marshall and asked, is there any way I could switch to study atmospheric physics at Imperial? And by pure luck, someone had pulled out at Imperial and he had a space. So I went up the following day to visit, and on the Wednesday morning resigned from Southampton and moved back to Imperial College. There were just 3 of us that year at Southampton, actually, who started in theoretical physics. There was me, another one who didn't show up, and the third, it turns out, is now the most highly cited black physicist in the world. So despite 2 of us pulling out within the first week, actually, it was one of their most successful years ever. Anyway, I returned to Imperial College. There I met people like Sonia Legg, Alistair Adcroft, and it was a wonderful group, actually. And another stroke of luck then is that John got a faculty position at MIT. So we all moved over to MIT 2 years later, where I learned an awful lot about about oceanography and meteorology. Then returned to a faculty job at the University of Reading in 1994. I had 12 happy years at Reading, but I kind of fell out of physics, I guess. At this point, I was in a meteorology department. Reading actually shut its physics department, which was a strange decision around 2005, I think it was, or 2006. And anyway, the opportunity came up to return to physics at Oxford, and I thought, you know, this was something I really wanted to do. And I've been in Oxford since 2007, back in the physics department, teaching physics courses, and never regretted doing that. So that's my background. I'll return to the role of physics and physicists, what you can contribute to oceanography at the end of the lecture. Okay, so I'm going to start today with a little bit of background. And so the slides today are based on a summer school from the lecture that I delivered last year. And if I had a bunch of students in the room, I'm not going to do this today. I would ask them to break up into groups at this point. So I like to show 2 figures here and ask, you can just do this in your head, but I'll ask you, how many eddies are there in each panel? And the typical answer I get in the left panel is 2, maybe 3 or 4. And in the right panel, somewhere between about 10 and 20. The reason I asked the question is these are from the same flow field at the same time. So one is showing what's known as the stream function. So basically the fluid flow is along the contours of the stream function at a speed that's inversely proportional to the spacing between adjacent contours. And then the vorticity is the curl of the fluid velocity, or del squared of the stream function. And the point I want to make is really that what you think of as an eddy often depends very much on which field you're looking at. And just to follow up on this point, then the second question I'd ask in a summer school, which is a question that was first posed by Ryan Abernathy in a paper 4 years ago, is eddy a noun or an adjective? And it's a great question. And the answer is really both. It depends on the context. So I think when we think about closed streamlines or closed circulation patterns, we're normally thinking of an eddy as a noun, as some sort of coherent structure. But often those of us working on parameterizing eddies are really thinking of eddies more in the adjective sense. So we think about eddy fluxes of heat, carbon, or vorticity, and so forth. So this is more to do often with these filamentary structures you can see forming in the vorticity field. Now, eddies in the sense of a noun, in the sense of coherent structures, definitely exist. I'm not going to say much about them today, but just a couple of slides to show you some of the better known examples. So here's one from the South Atlantic, so-called Agulhas eddies. And this is an example of what we call a western boundary current, the Agulhas current, that essentially runs out of coastline and then retroflects. And at this retroflection region, I hope you can all see my cursor here, but you then you have these eddies being shed and propagating into the Atlantic, Agulhas eddies. And a similar example, which occurs beneath the sea surface. So this is now dense salty water that comes out of the Mediterranean basin and flows around the south west corner of Portugal. And well, you don't run out of coastline here, but the current sort of tries to steer around the coastline, but some of the water is shed into these coherent vortices known as meddies, salty Mediterranean water. And here's a vertical section, and you can see a meddy of anomalously warm, but also salty water propagating out into the open ocean. So that is not the topic of my talk today. And what I'm really going to talk about today are the fluxes of quantities, such as heat, salt, and so forth, associated with these very fine scale filamentary structures. So this is a beautiful image from a very high resolution model by Jonathan Gula, showing us what we call the relative vorticity, the curl of the velocity field. And you can just see in this model of the North Atlantic at 1 kilometer resolution, an incredible richness of structure really at every scale that you look at. So you can see what we call these mesoscale ocean eddies here, with a characteristic scale of tens to maybe 100 kilometers or so. But even embedded within those much smaller scale structures that are the focus of a lot of attention at the moment, submesoscale eddies. It's kind of interesting, in the atmosphere, they would call these mesoscale eddies synoptic weather systems, and they call the submesoscale eddies the mesoscale. So it's interesting how different fields can have different names for the same concept, essentially. Okay, so I've got 40 minutes or so I've been allocated today, so I haven't got a lot of time to go through detail, but I'm just going to try and give you a very brief sort of introduction to where and on the scale and time scale on which eddies form in the ocean, and also the atmosphere for that matter. So the classic paradigm for where ocean eddies form and the scale on which they form is probably the ED model of baroclinic instability. So this was published in 1949. There was another paper that's very much more difficult to read by Charney at around the same time. But most of us, I think, prefer ED just for its simplicity and elegance. So what ED did was basically, well, he was thinking about the atmosphere, but this applies equally well to the ocean. So, imagine a slab of atmosphere. This slab of atmosphere has uniform rotation. It has uniform stratification. It has a shear in the vertical, so that means that the velocity is increasing with height. And well, this is a little more technical perhaps, but we have opposing potential vorticity gradients, as we like to call them, at the upper and lower boundaries. That's equivalent to basically saying that there are temperature gradients along the boundaries, the upper and lower boundaries. And this is one of the sort of classic, maybe advanced or undergraduate or early sort of graduate GFD problems, geophysical fluid dynamics problems. Not the easiest problem to solve, but you can show that the energy growth rate for the most unstable mode is basically a constant that's less than 1 times the Coriolis parameter. So this is twice the Earth's rotation rate times the sine of latitude divided by the buoyancy frequency, which is basically the square root of the stratification, and times the shear, so the rate at which the velocity is increasing with height. And if you put typical numbers in, you find that in the atmosphere, you get a growth rate of, you get growth over 2 or 3 days or so, which kind of fits with our experience at the timescale that weather systems grow in the atmosphere. And in the ocean, it's an order of magnitude longer. So ocean eddies will develop over about a month or so. And then you can also show in this analysis that the scale at which you get the largest growth is set by what's called the Rossby deformation radius. And this is basically set by the stratification, so the buoyancy frequency n, the depth scale of our fluid, and scales inversely with the rotation rate. And this comes out to be about 1,000 kilometers in the atmosphere, which again, it fits with our experience of atmospheric weather systems, or 50 kilometers in the ocean. So ocean eddies evolve more slowly and on much smaller spatial scales. So let's see how that works out. So this is a very old image you're looking at here of the variability in sea surface height, essentially. So the RMS variability in centimeters of the sea surface. And in the lower right, I'm showing you the energy growth rate from a calculation by Fulmer in Eden. And at least superficially, you can see there's a very strong coincidence of regions in which the ED growth rate is large and where we actually find eddy energy in the ocean. So at least superficially, the ED theory is working well. And then in terms of the length scales, well, this is a beautiful composite image. So you're basically looking at clouds in the atmosphere and you get a sense of the very large scale weather systems in the atmosphere. But superimposed then is basically a proxy for chlorophyll in the ocean. So this is the North Pacific here, the coast of Alaska, and you can see these much smaller scale ocean eddies on the eastern boundary of the North Pacific. So just emphasizing really that the scale is very much smaller. Now, the Rossby deformation radius is perhaps not the easiest concept to get your head around. So if I was teaching, I like to present 2 thought experiments, which may give you some intuition for where the deformation radius is coming from. And so what I like to do is think of a cylinder of dense water. You can do this experiment quite easily in the laboratory, or you could even do it at home if you want, and you've got food coloring and salt. So you get yourself a dense cylinder of water surrounded by lighter water, buoyant water, so a density difference. And then at time 0, we remove the cylinder that's holding that dense water up. And the question is, what's going to happen? And the answer is the obvious one, that the dense water will try and spread outwards and the buoyant water will spread inwards. And if you go through the maths, or you can just use dimensional arguments, because there isn't any other option here in terms of dimensionality, the speed of the current is basically set by the square root of what we call the reduced gravity, or the buoyancy, if you like. So gravity times the density, the fractional density difference, times the depth of the fluid. So the square root of that. Then you can ask the question, well, how far does this current get before it feels the effect of rotation? And it will feel the effect of rotation on the Earth after about a day or so, the rotation period, or in terms of our parameters, 1 over the Coriolis parameter. So basically that current will get a distance root G prime H over F, and that is the deformation radius essentially. So this is how far a dense anomaly can spread out before it feels the effect of the rotation, at which point basically the Coriolis force comes into play, deflects that flow, and you end up with a circulation around the dense water. And you've got Coriolis forces then propping up the dense water. We can then do the opposite thought experiment, and suppose this one you can't do at home, but suppose we had a massive cylinder on a scale much larger than the deformation radius, and we were to remove that. What would happen? And the short answer is not a lot. You'd have a little bit of slumping, but the deformation scale is so small that what would happen is very quickly the flow comes into what we call thermal wind balance, which is just another way of saying that the pressure gradients driving the density current are balanced by a Coriolis force. And so you end up getting a flow around the dense water rather than the dense water spreading out. And you get no sinking, essentially, of the dense water. So this is really the ocean limit and on the basin scale. And another way of thinking about this is if you go through the scale analysis, you can show that the ratio of kinetic energy to the amount of available potential energy. So that's how much energy could you release, potential energy could you release if you flattened these density surfaces. Turns out that ratio goes as the deformation scale divided by L squared. And so because L is very large here, essentially the potential energy is massive compared to the kinetic energy. So it's just impossible on this scale to convert much potential energy into the kinetic energy of eddies. But what happens in many situations when you go through the maths is that the fluid finds a way to break this constraint, and that's by basically becoming unstable at the deformation scale, because at the deformation scale, the ratio of kinetic and potential energy is order 1, and therefore it's efficient at that scale to convert energy from the background potential energy into the kinetic energy of eddies. So I realize this is a rather hand-wavy argument, but I hope it gives you some feel for why eddies form on this scale. Okay, moving on, and I realize I don't have the chat in front of me, so I'm just going to, I've got two screens here, so I'm just going to open the chat so I can see if there
You're
are
good
any
so far.
questions. Yeah, thank you. Okay, so parameterizing eddies in ocean models. So this is one of my favorite slides I've been showing for a very long time now. So this is sea surface temperature from two ocean models. So one is a model run at 1 degree resolution. You might call it climate or IPCC resolution. It's a model we ran in-house. I apologize for the quality of the picture, but you kind of get the idea. It's not a movie, but it shows you that you get a very broad sort of diffuse Gulf Stream in this model. This is the warm water moving up the western side of the Atlantic. If it was a movie, you wouldn't see an awful lot here other than the seasonal cycle and some wobbles, but certainly not eddies. And then in the right panel is sea surface temperature from a very famous simulation, quite an old simulation actually, by the group at that point at Miami. So MICOM, it's at 12th degree resolution, and you can see that the ocean is basically full of eddies. Wherever you look, you can see these turbulent features. So here's this very narrow Gulf Stream bringing warm water northwards, and you can see the flow breaking up into turbulent eddies. You can get an idea of timescale if you focus on the north-south migration of the temperature contours with the seasonal cycle. This is in reality on the right. So this is a composite satellite image showing us the sea surface temperature as seen from space. And superficially, at least, to the untrained eye, there's an awful lot in common between the satellite observations and the 12th degree model. So much so, there are instances on the web where this model is confused, actually, with reality, but it is model world. Now, if you were doing a course in fluid dynamics, some of you in a physics degree may do a fluid dynamics course. Not every physics degree does this, but we certainly do. You would learn that the relevant number here is the Reynolds number, which is the ratio of the velocity scale and length scale for the flow divided by the kinematic viscosity. It basically measures the ratio of the rate of change of momentum following a fluid parcel to the viscous acceleration. And the Reynolds number tells us whether we expect the flow to be turbulent. And the kind of rule of thumb is that for turbulence, you typically need a Reynolds number in excess of about 1,000 or so. In a 1 degree climate model, it turns out the Reynolds number is between 1 and 10. It's very easy to estimate this number actually for the ocean. In a 12th degree model, the Reynolds number is about 10 to the 3 to 10 to the 4. So we've undergone the transition to turbulence, hence the presence of eddies. In reality, the Reynolds number is about 10 to the 10, 10 to the minus 11. So, you know, it's 7 orders of magnitude larger than in a 12th degree model. But nevertheless, in fluid dynamics sense, I would argue that a Reynolds number of 10 to the 4 is a lot closer to 10 to the 11 than to a Reynolds number of 1 or 10. I also like to ask our students, if you could put your hand into these ocean models and feel what the water actually looked like, what would it feel like if you could actually pull some water out of one of these models? And for the 12th of the degree model, it's kind of interesting to think about, you know, what is the water that we're actually putting into these models? It's a very strange water, actually, very non-Newtonian, because it has a different stickiness, viscosity in the vertical and horizontal. So I'm thinking horizontally here. And it turns out, in terms of the actual numbers, the actual value of the viscosity, the closest fluid to the water in this model is peanut butter. So if you learn nothing else from this talk, you now know that if you have a big enough container, that even peanut butter can flow turbulently. And I often get asked, what's the water in a 1 degree model? I've never really found out the answer, but I suspect it's something like the sort of tar you put on a roof or something like that. It's incredibly sticky and viscous. Another interesting question to ask is, in terms of resolving ocean eddies, what's the equivalent resolution in the atmosphere to a 1 degree ocean model? So in other words, if we resolved atmospheric weather systems by the same number of grid points a 1 degree ocean model resolves ocean eddies, what would be the atmospheric resolution? And this is the answer. And I put this up just to point out that I don't think anyone would trust a weather forecast produced on a numerical model consisting of 18 by 6 grid points, but that's kind of, you know, what we're doing in terms of resolving ocean eddies in the ocean. So this emphasizes that this is an important problem. So certainly today, if we want to run ocean climate models on long timescales, but if you think about the sub-mesoscale, this problem is not going away, I would suggest, in any of our careers, whatever anyone tells you. Okay, so how do we parameterize eddies in ocean models? The vast majority of models use schemes, what we call an eddy parameterization. So a parameterization is a way of just representing the unresolved physics of the eddies. So we haven't got explicit eddies in many of these climate models. How do we represent that missing physics? That's our parameterization. And what used to be the case prior to the mid-1990s is people said, well, the eddies will just mix temperature and salt horizontally. The problem, apologize, I had a cold over the weekend and occasionally I'm going to start coughing, but hopefully it'll be okay. So the idea is that eddies just mix temperature and salinity horizontally. The problem with that idea is there are no significant sources of heat or salt in the ocean interior. So this introduces spurious sources of heat and salt and leads to all sorts of other problems. So Gentleman McWilliams came along in 1990 and had a different idea, and I'm going to present this in the way that they subsequently interpreted what they were doing in a 95 paper, one of the most important papers in our subject. The key idea is that fluid parcels conserve their density. So strictly speaking, some sort of neutral density, but let's not worry about subtleties of the equation of state and compressibility today. So this idea had been implemented some years earlier proposed by Reedy in 1982. And so here's a hypothetical ocean, a three-layer ocean, if you like, sort of warm, intermediate density and dense water. And imagine the fluid parcels are mixing properties along these density surfaces. It makes perfectly good sense because the fluid parcels are moving along these surfaces. The problem is, if we mix density along density surface, what does that do to the density field? And of course, the answer is nothing. And so Gentleman McWilliams noted that this cannot be a complete parameterization of what eddies do. because we know that eddies through baroclinic instability will extract energy from the mean flow. And that will tend to, if we're going to extract potential energy, then we're going to flatten those density surfaces. And so what they proposed was really a brilliant idea, is that we'll introduce an additional velocity into our models, an eddy-induced velocity, which acts to mimic baroclinic instability by basically flattening the density surfaces. And here's the detailed form. You really don't need to worry about it, but basically this is the important quantity here is some eddy diffusivity times the slope of the density surfaces. And so if the density surfaces are sloping, then this velocity field, eddy-induced velocity field, will extract potential energy and act to flatten the density surfaces. And most of the work that's been done since has really been trying to relate then that diffusivity to either the mean flow or more recently to the eddy energy as a prognostic variable in the model. That's the approach we're going to take. So just to illustrate this idea, so I was very fortunate to get into this game in the early days, and it was very clear to me at the time that people were having some problems trying to think about these ideas. So we wrote a sort of tutorial paper where we had a simple channel where we maintained a baroclinic front through heating and cooling, and then we drop a dye into this channel. And basically, I'm just going to show you what happens to this dye after, I think it was after 10 years. I can't remember the details now. And you can see that in the upper layer, actually, the yellow dye is spreading northwards across the channel. So this is not simple diffusion, where you'd expect a sort of the basin to fill with both green and yellow dye equally. But it's very much an advective signal where the yellow dye is moving northwards, associated with the tendency of eddies to try and flatten these density surfaces. And in contrast, in layer 3, it happens more slowly, but you can see the green dial is moving in the opposite direction. So this is very real, and it's important for the transport of properties such as heat, salt, carbon through the ocean interior. So the paper that really changed everything in ocean modeling was this paper in '94 in Science by Dana Basaglu, McWilliams, and Gent, where they implemented Gent and McWilliams in the NCAR climate model. And at a stroke, they resolved several known issues in ocean models. So one of the things they did is they removed this rather puzzling Deacon cell, as it's known. So this was basically an overturning cell that went from the upper ocean all the way into the deep ocean, which is kind of at odds with the density structure in the Southern Ocean, because this cell is crossing density surfaces. When you include the effect of eddies in this model, you find that Deacon cell largely removed. But they also found many other desirable properties. So they found, for example, that dense water formation, convection that was happening all over the place in the Southern Ocean, really associated with this overturning cell that's spurious, suddenly just started to occur in places that we knew convection was occurring in the ocean, but not over the wider Southern Ocean. And there were many other improvements too. And I think I learned an awful lot from this, because I think, and I don't mean this in any way to do down Gent and McWilliams, I think it was the seminal contribution of that period. But in a way, what they did was to remove something that was wrong. So in other words, by thinking about the conservation principles, conservation of the density of fluid parcels, they were able to make huge progress, because they implemented an eddy parameterization that didn't violate these basic conservation principles. And so that leads me on to the next part of my talk, and I'm going to try and give you an overview of what we've done over the last 15 years or so. And we call this geometric, so geometry and energetics of ocean mesoscale eddies and their rectified impact on climate. And I'll talk about something known as eddy saturation as well. So first of all, let me motivate why we care about eddies for climate. And this is just one example, but I think it's a very nice, clean example. So this is on the left is what I call an eddy permitting box model. So it was run by Dave Munday, a postdoc at the time of mine. And basically we took a very idealized ocean that's 20 degrees wide. So you can think of this as the Atlantic, if you like, basin. And then we have a re-entrant channel in the south representing the Southern Ocean, and we blew a wind over the Southern Ocean. Initially, we were thinking of trying to study the carbon cycle in this model, but actually it was really the physics that turned out to be more interesting. What you find if you put Gentleman-Williams, the parametrization used in most climate models, into this simple model, is that as you change the strength of wind forcing in the Southern Ocean, the strength of the current, the circumpolar current, goes up. It's what you might guess: stronger wind, stronger current. However, when we had explicit eddies, so at 1/6 degree resolution, and I'm being very careful here not to say resolved eddies, these are barely resolved at all, we found that in this model, and in fact many people find in other models, that there is almost no sensitivity of the transport to the wind forcing. So at least in this basic, I would argue this is a basic test, if you like, of our climate models. Do you get the right sensitivity of the circulation in the Southern Ocean to wind forcing? And the answer here is clearly no. Now, this matters because, for reasons I really don't want to go into, I guess, today, but it's called thermal wind balance. The strength of the current in the Southern Ocean circumpolar transport is very closely linked to how deep the density or temperature contours get over the oceans to the north. So basically, ocean stratification or ocean heat content is very closely tied to this circumpolar volume transport. So this really matters for heat and carbon storage on long time scales. So very much inspired by Gentleman-Williams, we set out to develop a framework for parameterizing and interpreting ocean eddy mean flow interactions. And I really wanted to focus on symmetries and conservation laws. I was back in the physics department at this point, you know, and thinking about classical mechanics. And in physics, you think a lot about symmetries. And so Gentleman-Williams taught me that you don't want to break the symmetries or conservation laws in the underlying equations. So if I can indulge in just a tiny bit of technical detail, so what we do is essentially we have our momentum equation and we introduce the eddy forcing as the divergence of a stress tensor on the right-hand side of our momentum equation. And all this is really saying is that eddies will transport all three components of momentum in all three directions. That's really all that this stress tensor is telling us. And it turns out that you can, through some mathematical trickery, essentially, represent all of the eddy forcing in the momentum equations, but that's a detail. And then secondly, and this is crucial, we need a consistent eddy energy budget. So any energy that we remove from the mean flow, because I remember our eddies are extracting energy from the mean flow in order to grow, we're going to put into a new variable we call our unresolved eddy energy, E, such that the sum of our parameterized eddy energy and the resolved energy of the model is 0, apart from explicit forcing and dissipation. So we have a consistent energy budget. We're not the only ones to have done this. Eden Greatbatch in particular been following this approach. However, I think what does make geometric quite distinctive is that it turns out the dimensional size of this stress tensor is bounded by the eddy energy. So you can construct a norm of that tensor, a Frobenius norm, and show that it's set by the eddy energy. And this is important because it means, if you think about it, all the remaining unknowns are dimensionless numbers, and it turns out they're all less than 1 in magnitude. And basically what these numbers do is they measure the shape of the eddies. So do the eddies have a preferred direction? And what is the tilt of the eddies then, both horizontally and vertically? And I don't really have time to go into details here, except to say that I'll say that when the eddies tilt with the background shear, which is the opposite of the eddy problem, then it turns out the eddies actually decay and accelerate the mean flow. But when the eddies tilt against the shear, as in the eddy problem, then the eddies are growing and will remove energy from the mean flow. You can actually diagnose these tilts in observations. This is a really cool paper by Stephanie Waterman. And actually, if you want an intuition for this, just look at the giant planets, Jupiter, because you can see the tilt of the eddies in the clouds on Jupiter. And you can see very clearly that the eddies are anisotropic in many regions, not all regions, but many regions. There's very strong anisotropy. And you can see by eye from the tilt of the clouds what the tilt of the eddies is. And in fact, you can formalize the link of this, the tilt of the clouds to these eddy angles. In the ocean, it turns out what's most important is actually the vertical momentum fluxes. So the flux of zonal momentum vertically. So from the sea surface down to the sea floor. And this is what we call an eddy form stress. And basically it comes about when you've got, imagine you've got two density layers, a light layer and a dense layer. And you can, through pressure forces, you can have the light water push against the dense water. So if you have your pressure anomalies, as I've sketched here, then it turns out that the pressure gradient acceleration is one direction in the light water and in another direction in the dense water. And effectively what you're doing is taking momentum from the upper layer and moving it downwards. So this is what we call the eddy form stress. And just to give you an idea in geometric then, what our mathematics tells us is we'd have to represent this form stress as an unknown non-dimensional number times Coriolis parameter over the buoyancy frequency. So we know these times our eddy energy, which we're going to model. So if we have the eddy energy, the only freedom is to specify alpha. I'm also a pragmatist, so we can force this to look like Gentleman-Williams. And if you reverse engineer out a Gentleman-Williams diffusivity, then you can derive this form here. I won't say any more, I think now. So the only freedom is to specify a non-dimensional number. So I'm going to show you 3 proofs of concept of this idea. The first is a textbook problem. So this is the one that you might get in an advanced undergrad or graduate exam, but we're now going to solve this using geometric. And there's so much symmetry in ED that geometric is beautiful in this for this problem. There's so much symmetry that you can carry all of your constants through the integral because everything's a constant, essentially. The shear is a constant, stratification and F are constants. And so you can very easily show that the eddy energy grows at the following rate. So it grows exponentially at this rate. And that is the ED growth rate if alpha is 0.61. So I don't know what alpha is from geometric. I happen to know because we can solve the problem analytically. It should be 0.61 for this problem. But apart from the value of alpha, geometric guarantees that we keep the right functional form of this for the growth rate of the eddy energy in this analytic solution. Now, of course, the real world is nonlinear, so we need to then go to numerical solutions, but we can play the same game in a numerical model. So this is now a fully turbulent ED calculation, if you like, that Scott Bachman ran for us. And what we're going to do is compare the eddy diffusivity we diagnose from the model by essentially dropping dyes into the model and measuring how quickly they spread against what geometric predicts. So y-axis against the x-axis. And this is what we get in the model. So perfect agreement would be this dashed line. And believe me, this is a lot better than any of the other parameterizations that have been proposed here. So there is an offset, and basically what happens is alpha is about 0.2 in the turbulent regime, and it's 0.6 in the linear regime, as we saw on the previous calculation. But apart from that non-dimensional number, geometric is doing a really good job. However, the result that got us really excited is it turns out if you do the calculations I've just shown you previously for eddy saturation, so where you vary the wind stress over the Southern Ocean with geometric, then we can reproduce eddy saturation. So in other words, with geometric, when you increase the wind stress over the Southern Ocean, you get almost no sensitivity of circumpolar volume transport or ocean heat content to wind forcing. And why is that? And it's kind of interesting that it goes back to basic physics. And, you know, my God, we filled pages and pages of algebra getting to this point, but it comes down to a momentum budget, essentially. So the wind stress is balanced by this eddy stress that's transferring the momentum downwards. but in geometric, that just scales with the eddy energy. So the wind sets the eddy energy. And then the energy budget, well, the source of eddy energy must balance the sink and equilibrium. The source is basically the eddy growth rate times the eddy energy, and the sink is the eddy energy divided by the damping timescale, so presumably set by frictional processes. So basically, the eddy energy factors out, and when you integrate, the transport of the current is set by this frictional damping timescale. So it's the energy budget that sets the strength of the current, but it's the momentum budget that sets the energy. It's a classic two-dimensional dynamical system where you've got this interplay between the two. And an interesting curiosity is that the current turns out to be anti-frictional. So as you increase the bottom drag, the current gets stronger. And that's kind of weird, but it's what we predict. And that's because stronger friction acts to dissipate eddies. And if you remove the eddy energy, the current has to get faster to bring the eddies back. And you always need the eddies because they're an integral part of this story because it's a coupled dynamical system. So it's very counterintuitive, but kind of cool. So we've implemented this in a global model. I won't go through all the details of what we do with the eddy energy. This is what you find in a high resolution model for the depth integrated eddy energy. This is what we get in our parameterization. It's far from perfect, but you know, we get the main hotspots of eddy energy in the Southern Ocean. We do less well in the regions where the eddy energy is lower, I'd say, but in the crucial regions, we're getting the right sort of patterns. And the punchline is we find that pretty much every current in the ocean is sensitive to this eddy energy damping timescale. So not just the Southern Ocean circulation, but even the overturning circulation in the North Atlantic in our model is acutely sensitive to this timescale over which we dissipate Southern Ocean eddy energy. And that's basically because we're affecting global stratification, and that affects many other currents. And so this really has led us to rethink the whole sort of theory of the Southern Ocean circulation. If you go to any textbook, they'll tell you that the circumpolar current is wind-driven or driven by a combination of wind and buoyancy forcing. Well, we find that the circumpolar current is insensitive to the wind stress, so that's wrong. In my mind, what we actually find, we go through the maths, is that the circumpolar volume transport is set by the deformation radius, the width of the current, and E-folding depth of the current, our non-dimensional alpha, pi. We can blame Dudley Chelton for pi because of the way he defines LD, and 1 over this eddy timescale. So it's kind of nice. It's 3 length scales divided by a timescale. And I think I'm short of time, so I'm going to skip over how we estimate the numbers, but you can do this from observations. And given that this formula is so different to anything I've seen before, I find it kind of amazing, actually, that you get out the right order of magnitude. It's about 10 to the 8 meters cubed a second, or to use ocean jargon, we call that 100 sverdrups. I don't want to claim any more than one significant figure here because, you know, this is scaling analysis really, but we're in the right ballpark and, you know, I think that's encouraging. So I want to wrap up on the science. So the ocean's populated by an intense eddy field, equilibrated ocean models. And I mean, you need to run these models for 3,000 years or more to really come into equilibrium. So for paleoceanography or long time scales, you know, this is not going to happen for the foreseeable future that we resolve eddies routinely. And if you're going to get to the sub-mesoscale, I think for climate modeling for decades to come. So I think development of eddy parameterizations is necessary, but it's also useful for testing our understanding. I think recent advances are challenging some of our existing paradigms. That's what we do in physics. We always question. We're explaining phenomena such as eddy saturation, but there's an awful lot left to do. This is the turbulence problem, and no one is going to solve this problem anytime soon. It's been around for too many years. But there are huge numbers of opportunities for physicists to contribute. So I just want to end with a few more slides. So one is something I'm working on at the moment. Rosie Eves is in this talk, this seminar today. But she's been working on a different paradigm to Jensen McWilliams that's been around for years, but no one ever implements, called potential vorticity mixing. And the idea is that fluid particles conserve this quantity called potential vorticity. It's basically, you can think of it as related to angular momentum conservation, if you like, spin angular momentum. Let's leave it at that. And it's quite important because if imagine you do freely decaying turbulence over topography, then it turns out that the eddies don't spin the ocean down to a rest state, but generate quite strong currents along the topography. And a potential vorticity mixing closure will produce the right sense of the answer, but it gives you way too strong a current. And the reason is that basically the state of uniform potential vorticity has huge amounts more energy than is available in your initial state. So what you need to do is constrain potential vorticity mixing. So this is a calculation over topography with explicit eddies. And you can see here, what's happening is that the mean kinetic energy is actually increasing by extracting energy from the eddies. So the opposite of baroclinic instability. And Rosie's got a nice approach by carrying both an energy budget and what we call potential entropy budget, which is basically potential vorticity squared, that you can then use to reproduce the sort of results that you see with explicit eddies. And we're currently trying to figure out how to apply that now to the Arctic, where it might be important. Those of you who are physicists, you may not have heard of pseudo-energy, but you may know about Lagrangian Hamiltonian dynamics, and conservation laws are related to symmetries. And one trick you can play in Lagrangian mechanics is to average your equations in time. And if you average your equations in time, then you kind of average over the eddies, if you like. So we kind of know when we've averaged our equations that energy is not conserved because eddies can extract energy from the mean flow. However, you may still have a time symmetry in your problem. And it turns out that there's still a conserved quantity, but we call it pseudo energy in that case. And it's very closely related to what's going on in these calculations. If you like your maths, and I saw Steve Griffiths in the audience, he likes his maths, I know tensor calculus, and so does my former colleague, James Madison. You can do lots of maths on these problems. And James wrote a beautiful paper, which came about from a throwaway remark by me. Why do our results depend on the coordinate system? We don't do this in general relativity theory, for example. I had no idea what I'd unleashed on when I set James off on this. But one nice thing he did, it turned out there were 5 different stress tensors, if you like, in the literature, and they all looked different, and it was very puzzling, which one is correct. Turns out there's so much gauge freedom because what matters here is the double divergence of this tensor. It turns out they're all equivalent, and we even added a 6th tensor, which actually is the one that's diagonalized and has the tightest constraint on its magnitude. So if you want to do your theoretical physics and maths, there is a lot of scope on this. And this was the easy version. James then went off and extended this to thickness-weighted primitive equations, as they're called, which is, ends up looking like general relativity theory. And it was kind of hairy, but a lot of fun to be involved in it. And then a paper that we're about to submit on a simple 2-dimensional model of the Antarctic circumpolar current. So this is putting time derivatives on the model I showed you earlier for eddy saturation, essentially. It turns out that without one of these terms, a small term on the right-hand side, this system is Hamiltonian. And so you can use something known as action angle coordinates, which I was teaching about literally 2 weeks ago to our undergraduates. And you can use action angle coordinates to map out the periods of the oscillation just from the Hamiltonian phase portrait. And then what you can do is you can excite the dissipative, weakly dissipated Hamiltonian model with stochastic forcing, and this brings you into the realm of fluctuation dissipation theorems. So I'm just trying to give you a flavor here that, there's a lot of basic physics you can bring to bear if you've got that in your toolbox. So if you are in physics, please don't think it's all number crunching. We need people who can think about the problems too. And I should have said here that although this is stochastically forced, the period agrees very well in stochastically forced integrations with the Hamiltonian prediction. I wanted to end by talking about education. So I spend a lot of my time these days running a very large graduate program. So we have over 100 graduate students spanning all of environmental research at Oxford. We do an awful lot, building a cohort across different disciplines. It's very multidisciplinary. We've done an awful lot to increase diversity and to make Oxford attractive to people who might not have considered coming to Oxford. I was one of those people 30 years ago, so I really get this. And I think this is really important, and it's actually making a huge difference, to be honest. We found that in our latest admissions process that so one of the students in this video is coming to Oxford, and that's great. However, whilst multidisciplinary science is important, I think one thing Oxford does well, but does worry me in general, is we also need disciplinary excellence, and let's not forget that. And I'm going to end with a paper, an article that really inspired me a lot 30 years ago when I was finishing my PhD by Peter Rines, called Physical Oceanography, Old Friends, New Agendas. And he was talking about how we really, as a field, had to rise up to address the new agendas. So climate change, paleoclimates, incorporating the physics and the biogeochemistry. I guess these days one might think about new technologies too. So machine learning, it's a great opportunity and there's an awful lot of good things we can do. But I think there is also a threat there, and what we've got to be careful of, and this is what Peter Rines was pointing out, is let's not throw away the tools that got us to this point in the first place. And a lot of those tools are the fundamental geophysical fluid dynamics, or to put it in another language, the basic physics that we all learn about in physics degrees that really underpins our science. And I really want to end with that thought. Whilst we quite rightly move towards a multidisciplinary future, please don't forget that if we're going to address these multidisciplinary challenges, we need to do it from a position of disciplinary excellence. And we really need the physicists, as well as the chemists, the biologists, so forth. But physicists have a big role to play in moving this subject forward. So thank you very much.
Thank you, Devin. Are there any questions? If you can either
I
pop
will
them in the
stop the
chat.
share, shall I?
Oh yeah, that'd be good. Stop the recording.
Then I can actually see people.